Hello everyone, I'm Collins Olukwu and this is my ENCMP 100 programming contest submission. The inspiration for this project actually came from a future project where I aim to simulate the famous SpaceX rocket landing using a bipropellant powered rocket. In order to carry out such landing, I need to be able to accurately predict and model how the center of mass of the rocket changes the reflex, the thrust slash energy produced by the rocket, and other factors. Now, at its core, all of this just boils down to solving a series of ordinary differential equations that governs how this element changes over time. So with that being said, I started with version 1. Now for version 1, this version was relatively simple and was mainly just for me to understand the maths from ground up. In this method, I implemented an Euler solving method where I allowed the user to enter in their input and variable and doing some simple calculations and got all the points on the curve and plotted those points. Now, some of the problems I had with this version was that the main problem being that the user couldn't enter in friendly expressions and had to rely on the standard Python expression, which could be a bit annoying to type. And second, the Euler method is mainly insufficient for stiff differential equation. So I moved on to version 2. Now in this version, I entirely ditched the manual solving of the differential equation and instead decided to use SciPy to handle the solving as it was more optimized and generally better than manually solving the differential equation. Now for this met- Now for this version, I also added in backward solving capabilities in the sense that if the user enters in a starting value earlier than their initial conditions, the solver won't just scratch but actually plot those values. But now some of the issues I was still having with this code is that the bunch of import statement I had at the beginning of the code was making the code a bit untidy. And also I also wanted to add a tailored polynomial fitting option. Number on to version 3. Now for this version, the main improvement I made was adding a tailored polynomial fitting option in which the user gets to enter in their degree and precision they want the tailored polynomial fitted, and this automatically fits the tailored polynomial onto the curve. In this version, I also cleaned up my code a bit by moving all import statements to a separate Python file called modules. Some of the main issues I was still having with this code was that I used a lot of global variables to achieve this, and this made my code and my functions more dependent on each other, and could lead to more issues later when trying to modify the code. Also, there also no form of error catching in this code, so I also had to implement that. For my last and final version, I first started off with removing all global variables and passing in these values as parameters into the functions instead to make my code more and my functions more independent of each other. Now, nextly, I also added a file saving function that allows the user to save in both the plot and the Taylor's plot and the Taylor polynomial for any future references. Then I made the code more user interactive, in which the user gets and have much more control over the program flow and which specific solver method is used in solving the differential equation. And I'll say the major improvement I made in this version was lambdifying to the expression only once and passing that value as a parameter instead of lambdifying for the thousands of iterations of the loop. Now some of the issues I still have with this version is that the error checking mechanism is not as robust and it could be made and it could be improved. So now to round up, what did I learn from this experience? Well, the major thing I learned was when moving from a manual solver to SciPy. This taught me the importance of using existing libraries rather than trying to reinvent the wheel and coming up with your own custom libraries slash solver to handle the task. Secondly, I also learned a bit about defensive programming where you anticipate where your program might crash and build a safety net around those those failure points so that the user never gets to see the program crashes. Thank you for taking your time to listen to my submission.